Hi, this is Mr. Manley. In this video, we are going to take a look at some applications of PowerSeries. This list of equations might look a little bit intimidating, and you can find lectures about how these are derived and make quite a bit of sense out of them. But don't be intimidated by them. The actual application of these is pretty straightforward, and that is what I'm going to look at here today. I'll just say at least one thing, maybe a couple of things about these. These series here, these are Taylor series, and you would find that you spend a little bit more time with these if you take calculus. You'll have a section on Taylor series. And this equation down here, I would like to look at and just notice that. So I'll give you a little bit of the derivation that if I were to let x equal I theta in this series, I would be able to condense that down to e to the I theta. So I let x equal I theta, like I said. And then that we would actually find out is equal to cosine theta plus I sine theta. A little bit more detail than I would want to take going into this here, how we get that. But do notice that if I put in an I theta for all these x's, that we would be able to find the sine expression in there, and we'd be able to find the cosine expression, and then that would all condense down to the cosine theta plus I sine theta. So maybe I shouldn't have mentioned that. Maybe that's just confusing, but it's rather intriguing combination of these three series to get to that point. So I did want to mention it. And also it's going to help us lead down to here. Before I get to that point though, I want to do another substitution, and I want to let theta equal pi. And then when we let theta equal pi, we get e to the I pi is equal to, now I won't actually write this out. Let's just think about this though. I'm going to put in theta is equal to pi. So what's cosine pi? Hopefully you don't have to think about that too much and get that that's -1. And then if I put in theta as pi here, I have sine pi. And what's that? Sine of pi. Again, hopefully you don't have to think too much about that, but that's 0. And then if I simply add -1 to both, or I add 1 to both sides, and I get +1 on the left, and -1 plus 1 is 0 on the right. And that is quite intriguing as well. That here I've got an equation that includes these 5 foundational numbers from mathematics, e, I, pi, 1, and 0, all converging into this one equation. And isn't that interesting? Quite remarkable. So I did want to show that. And then finally, where are we going to get? Let's go back up here after that little detour and say that another thing that I know is that z is equal to r cosine theta plus I sine theta. And that's from work with complex numbers. That's the trigonometric or polar form of a complex number. Well, look what happens here is that I can divide by r. So I have z over r. And then I've got this match here. Well, let's look at it like this. I've got that matching with that cosine theta plus I sine theta, so I can do the substitution. I can substitute this on the right side of this equation down here, right? And look at what happens when I do that. I get z over r is equal to, and then I make my substitution, e I theta, and then simply solving for z, well, I don't need to write it out because I have it right here. Solving for z, I get z equals r e to the I theta. And here we have what would be considered, or what was called the exponential form of a complex number. And compare that, or consider that we also have the rectangular form of a complex number, which is the first form that you learned in intermediate algebra, z equals a plus bi. And then we've also got finally the trigonometric or polar form of the complex number here. So if I go back to this original state here, this original equation as I wrote it, it's not too messy. I think you can see z equals r. I'll just rewrite it. Z equals r cosine theta plus I sine theta. And we want to be able to move back and forth between these three forms. So we have that form, and that form of a complex number. And we want to be able to use all of these interchangeably. And that's where some of our work will take us. Finally, I think I just want to add one more element here, right? If I were to take, let's go back to our magical little equation there, e to the I pi, and let's take it back to the form that we originally solved in, equals -1. And then how about if I convert that to trigonometric form? ln -1 is equal to I pi. So that may take you a little bit of review for a moment to think about, how do I convert from exponential to logarithmic form? But that is certainly what we can do with the definition of a logarithm. And that is in fact what I have right here, right? ln -1 equals I pi. And we're going to use that as well. So don't be too intimidated by all this again. I mean, these are given. So we're given this, we should know this already, know that already. You're given this, you're given this. And given all of that, we want to have some applications for PowerSeries. So let's just go ahead and take a look at what we could be asked to do. For instance, we could be asked to do, what's the sine of pi? Let's say 11 pi over 12. Maybe a student would want to enter that into a calculator. Probably a typical student of pre-calculus would want to do that. A fairly atypical student might recognize, I can rewrite that into a sum or a difference and use the sum or difference formula for sine or cosine. And finally, we have what our business is here today, which is using this series here, using this. Now, if we're going to use that, of course, that's an infinite series, and it would need to be specified exactly how we're going to use this. So for instance, we might say that we are going to go 11 pi over 12 minus 11 pi over 12 to the third over 3 factorial. And continuing, we can get a few more terms. And if we're going to use this series to evaluate this, it has to be specified. So this it might be specified to find using the fifth partial sum, which simply means that I want to use 5 terms. And you can see that I've got 5 terms there. And then that becomes a calculator entry. And when I enter that into the calculator, I get .25882. No, that's what I would get if I enter this into the calculator. If I enter this into the calculator, if I enter that, then I'm going to get 0.261505. So in order to get this number here, we have to use the series. So if you're asked for the fifth partial sum, you can't just enter sine 11 pi over 12 and hit the key and get the answer. You're going to have to do 5 terms. That doesn't seem like anything that makes sense to do today, and it probably doesn't, but it does emphasize the power series. And just imagine, before we had calculators or these little handheld computers that were so powerful, the power series was absolutely necessary. And then, of course, there are going to be applications of power series where we're not really interested in it numerically, and we want to be able to have some familiarity with it. So that's one thing that we could be asked to do from this list of equations. Another thing that we could be asked to do would be to write this number in exponential form. So what do I have here? I've got a number that is actually in the form a plus bi, right? What's going on here? A is 0, and I, or b, is -2 rad 6. So that's a rectangular form of a complex number we've been given there. And then we're going to be asked to convert this to exponential form. All right, well, what's the exponential form? It's z equals r e to the I theta. I need r and I need theta. What I like to do is look at these graphically and go, all right, this is the real axis, this is the imaginary axis. I've got 0 on the real axis, a -2 rad 6 on the I-axis, which would put me down. So the number is, say, here. And then what do I need? I need r. Well, that's r, the distance. Never give the distance a sign. It's not plus or minus. It's not directional. The magnitude, the r, is simply an absolute value. So I've got my r for this number in exponential form. The r is 2 rad 6. Again, no negative. And then I need to go e, I, and what's the angle? Well, I can see the angle right there. I don't have to do any solving or exploration here. I just see that it's 270 degrees, but we're not going to ever say it in degrees. We're going to express this in radians. Okay? So there's converting from the rectangular form to exponential form by simply finding the magnitude and the angle. Okay, likewise, we could be given a number in exponential form and say write this in rectangular form. So going the other way. And what I would like to think about here is just, I'm going to convert first to the polar form. So that's going to be magnitude r times cosine of the angle plus I sine of the angle. That's polar form. Now to get to rectangular form, I simply multiply that. So rad 26 times rad 2 over 2, that's cosine pi over 4. And then I've got I, rad 26, again, sine of pi over 4 is also rad 2 over 2. And simplifying those, I get rad 13 plus I rad 13. And that's the rectangular form. Actually, I have all three forms there, right? I've got the exponential form here, the polar form here, and the rectangular form there. Okay. Okay, so here's one last problem to look at. Say I've got e to the 2x plus 5e to the x plus 4 equals 0, and I'm asked to solve for x. Well, this is really a question of algebra, right? I see an algebraic expression, it's a trinomial, so I want to be thinking factor. And factoring, I'm going to use FOIL. And then from there, I've got the zero product property. So I can say e to the x is negative 4, or e to the x is negative 1. And then using the definition of a logarithm, I can write these two. X is equal to ln negative 4 and ln negative 1. Which up until this lesson, maybe up until this video, you thought, well, not interested. Those aren't real. But now, today, we see that, yeah, they're not real, but it's still a solution. We can do the logarithm of a negative number. The logarithm of negative 1 is I pi. So let's use that here. And we're going to use a property of logarithms here. ln negative 1 times 4, which is ln negative 1 plus ln 4. Remember that property of logarithms? The multiplication property of logarithms. And as we just saw a few pages ago, ln negative 1 is I pi. And then we'll leave that as plus ln 4. Comma, this will just come down as I pi. So now we are responding to the question about a negative logarithm. And where would we have some application of this? We could have application of this in electrical engineering. Anytime we see I used in mathematics, that's a place that my mind goes. Also physics is another place where we might be seeing these values of I are actually telling us something about the physical world, even though they are conceptually difficult to grasp.